how this fits in is we have these series of episodes, and my assumption is that the speakers in the subsequent episodes will provide a lot more detail about each of the realms that I'm going to talk about. And so this is really just a high-level overview. I'd also like to thank Christine Foreman. She gave me some really cool slides. You all for tuning in, and of course NSF, because they fund a lot of the Antarctic work in NASA, for organizing this really cool group. And I apologize for being underprepared. I would have liked to highlight a lot more work. Okay, so the cryosphere. This is the portions of the Earth's surface where water is in its solid form. And there's a huge diversity of solid forms of water on our planet. It includes sea ice, lake ice, river ice, snow, ice sheets, and glaciers. Let's see. Still getting used to this thing, sorry. I won't have time to go over every one of these realms. I'm going to focus on ice sheets and glaciers primarily for this talk, because I think that's most relevant to ocean worlds. Okay, so why are we interested in studying cryosphere ecosystems? And I think this translates across both planetary and earthbound cryospheres. So even though we've been studying them for decades, we still know very little about the structure and function of icy ecosystems, particularly the microbial communities within them. On Earth, the cryosphere is really a vital part of our biosphere, despite the fact that we know so little about it. And it's because the cryosphere can support diverse communities that are metabolically active and have important functions. So they serve these ecosystem services, or perhaps even disservices in some cases, in the active portion of these microbial communities. And this is a topic I'll try to touch on in bioalbedo. They also participate in global biogeochemical cycles. Ice and its associated landscapes are also really important repositories. They collect and store a diversity of materials, including biomolecules, other signals of what past climate might have been like on Earth, and evidence of what the depositional regime was at the time these materials were collected. And especially for this community, they also serve as really important modern analogs for past ecosystems on Earth, as well as provide potential insights for fugitive ecosystems on these icy ocean worlds. Can't use that key. Okay, so permafrost. I'm not going to really talk about permafrost, even though it's fascinating and has potential relevance for ocean worlds. This is where part or all of the water in a soil matrix is frozen year-round. It does encompass about 25% of the northern hemisphere. And the big thing about permafrost on Earth is that it stores a significant amount of carbon. And so we have a lot of interest in what the fate of this carbon is. So because I'm not going to have time to get to a lot of these topics, I am trying to highlight a couple review articles so that folks who go back to this recorded talk can look those up and get some more insight. Okay, so snow. Snow is where the cryosphere basically starts. This is what precipitates and accumulates the large chunks of ice that we have on our planet. And microbes actually play a key role in the formation of snow, and they're also broadly transported around the globe in these snow particles. And so because of their ability to create proteins that interact with the ice matrix, they can nucleate snow at much, sorry, getting a lot of notifications as I do this. So they can nucleate snow crystals at a higher temperature than some other particles like volcanic dust can. So they're an important player in that. They're also an important key component of artificial snow. It's actually proteins from microbes. So for those of you who like to ski in regions that are diminishing in their snow, artificial snow is a big component of that. The next significant part of the cryosphere, and I don't know if you guys can see my pointer here, but I like this really cool picture because it kind of spreads out all of Antarctica and the rest of the world in this unique way. But you can see that sea ice tends to form annually in the North and South Pole. And sea ice forms directly from the ocean. It forms, grows, and melts in the ocean. It covers about 25 million kilometers squared of the Earth. and 15% of the world's ocean is covered with sea ice at some point in time. And this is a highly variable feature, and it has important impacts for the Earth's albedo. It reflects more sunlight. When it's extensive, reflects less. When it's not as present or when it's dirty, in quotes. And it's an important habitat for a diversity of life forms. This is the one or two images of the charismatic macrofauna that I'll share with you guys, but it serves as an important place for hunting, nesting, and resting for organisms like polar bears and penguins. But it also is a home for extensive ice algae, and these are communities that serve the entire food chain through their productivity. Yeah, so, and I highlighted over here, Jody Deming and Karen Young. Karen Young is a part of the NOW network. Their research groups do a lot of work as well as others in sea ice, and there'll be a lecture on this later. But the important part to note is that in addition to servicing the rest of these marine food chains below the sea ice through the extensive formation of these algae, these organisms also produce a lot of extra polymeric substances which could actually interact with and shape the structure of the sea ice. Okay, so moving on to glaciers and ice caps. And these form when snow accumulates long enough in a region to compress and form a thick ice mass. Currently, about 10% of the Earth's terrestrial surface is covered with glacial ice. This includes glaciers in more temperate regions, ice caps, ice sheets in Greenland and Antarctica, and about 69% of the Earth's fresh water is in these glaciers and ice. This number, this percentage, over the course of my career, I've noticed it shrinking significantly. I think in my textbook it was like 75%, so this is a noted loss. And I'm going to go into a little more detail in the glacier and ice sheet ecosystems because I find these really fascinating. And these can be divided into three broad realms. The superglacial realm, which is the surface realm, the endglacial realm, which is within the ice matrix, and then the subglacial realm, which is at the base of a glacier. So I'm going to go through each one of these we'll see what kind of time I have to kind of talk about some of these different systems. So first is superglacial. Again, since I don't know that I'm going to get to cover this in sufficient detail, here's some of my favorite reviews on this that really describe how glaciers, although we didn't used to think this way, are really ecosystems in all of these realms. Okay, so first the superglacial realm. This is where we find diverse, highly pigmented organisms that find a home on the glacier and ice surface. This includes the snow algae. These have been in the news a lot lately. These are these highly pigmented, bright snow algae like Chlamydomonas. There's also a diversity of bacteria that form diverse pigments that can serve for UV protection. Microbes also contribute to the formation of cryoconite holes on the glacier surface. And these are these dark holes that form especially in the higher latitudes where you have sediment and microbes melting into the glacier. And this has become a subject of interest because the coloration of the bacteria and algae can change the albedo of the snow, and this has been called bioalbedo. And as you can see over here, this figure from Martin Trentner, he shows how there's a different albedo shift depending on the type of pigments that the various algae have. And so this is a significant way with which microbes interact with the surface of the glacier and affect its overall hydrology. In the endglacial realm, this is one of the trickier realms to study. This has typically been the site where we've collected ice cores to look for deep time climate records. And so this is where we've looked at the concentration of atmospheric gases within glaciers, but there's also the accumulation of dust. And with those dust particles, we also find a variety of biomolecules and microbes. And so ice cores need to be handled with particular care because you're looking at particularly low biomass and particles. And so here are just some examples of the deep core collected from Waste Divide. Montana State University has a novel sub-zero facility that you can manipulate these ice cores with for study. And we find that many of these the abundances of microbes track with the dust and other materials that we see within the different layered deposits that represent different periods of time. So for example, here you see the abundance of microbial cells and how that varies with depth, which is equivalent to time in the ice core record. Microbes also don't fit in the ice matrix itself, and so they tend to squeeze into ice vein structures. And here in this really cool image by Christine's group, you can see here's microbial cells that are forming along the ice vein between two different ice crystals. And so this is one place where microorganisms can be stored, if you will, in these deep cores of ice. And one of the ways that they might survive is through some of their unique abilities to interact with the ice structure. And this is not only forming extrapolymeric substances, which is like a goo of carbohydrates and other biomolecules that might protect them from the ice matrix. They can also form proteins that specifically interact with the ice structure itself and can prevent that ice from stabbing and otherwise damaging their cells. Okay, so moving on to my personal favorite, the subglacial realm, which is situated beneath the ice sheets. And I find these areas really fascinating because they really are highly diverse, even on Earth. You have hypersaline subglacial lakes, such as the recently detected subglacial lake in Devon Island in Canada. You have caldera lakes that form below ice sheets, such as Grimsvötn in Iceland. And in Antarctica, we know of almost 400 subglacial lakes that have been detected so far. But again, we haven't really been able to drill through the ice that extensively, and so we still know pretty little about these lakes. But you can imagine when you lift up something the size of the Antarctic ice sheet that there is a tremendous amount of diversity, both in subglacial lakes, but also saturated sediments and streams that exist below these ice sheets. And so, yeah, I'm just going to quickly go through some of these diverse habitats that we see below the Antarctic ice sheet. Lakes are a really important target because they're large bodies of liquid water that can affect ice sheet hydrology, and they also, if they're closed basin, can serve as a repository for sediments. We have these closed basin lakes that accumulate materials, but then we also have these active interconnected lakes where the water drains subdecadally through below the ice sheet into the ocean. These can serve as sediment repositories. I was talking about these closed basin lakes, and for example, in subglacial Lake Ellsworth, about 6 meters of sediments have been detected by radar surveys. Sediments have been collected from some lakes, such as subglacial Lake Whillans and subglacial Lake Mercer, and these sediment cores have been analyzed for microbes. Whoops, backwards, forwards. We also have debris-rich basal ice at the base of the ice sheet. This is technically more challenging to collect, and so we have less studies done from the interior of the continent, and most of the work on basal debris has been done along the margins where you can actually access it by walking up to it. Below some of these ice sheets, there's also extensive sedimentary basins, and these can have hundreds of meters of sediment that are likely rich in organic matter. These are ancient marine sedimentary basins, such as the Wilkes Basin. And there's also groundwater that's been detected below some areas of below the ice sheets, and we know very little about this groundwater and how it slowly leaks to the ocean around it. But we do know that in all the subglacial samples collected to date, although there have been very few, we found active microbial cells, so cells that we can detect by microscopy, that we can cultivate, we can extract their nucleic acids and try to better understand them. We can also measure their metabolic activity. And so there seems to be some commonalities, again, in the very few subglacial environments that we've sampled. They appear to be largely chemosynthetic, so they can fix inorganic carbon in the absence of sunlight. And it seems to be enough to sustain the heterotrophic needs of microbial communities that exist with these chemosynthetic organisms. These organisms appear to get their energy from compounds like ammonia, sulfur, and iron. So it appears they're utilizing redox reactions, doing rock-water chemistry, rock-powered life. The phylogeny, the diversity of microbes that we see, seems to reflect the chemistry that we expect in that system, as well as what we think the pre-glacial history may have been. And it seems these organisms play a role in subglacial weathering, and many appear to be cold adapted, which makes sense. And so while we've studied very little, what we can say is that these systems are also very diverse. Although they may have common attributes that we would expect of something that lives in complete cold and darkness, there's also a lot of variation. For example, subglacial Lake Willans is relatively fresh. It's at the pressure melting point. It has a high level of diversity compared to other subglacial settings, but it's actively discharging, so potentially less stable, versus a place like Blood Falls, which is another subglacial environment on the other side of the continent, which is slower moving, so appears to be more stable. It's 2 to 3 times the salinity of seawater, and it's much colder. So I just show this to highlight the real potential diversity in these types of systems. It seems that hydrologic variation is a really important driver that shapes the type of life we see in these systems. And this is because melted water, if you have active melted water, it can deliver oxygen, which is an important electron acceptor. And in the absence of active hydrology, you might close off the input of new oxygen to your system and drive it into anoxia and push it to use different electron acceptors in its metabolism. Hydrology will allow for different solutes to accumulate or not, may or may not disturb, accumulate organic matter. So subglacial environments have it all. It's a dynamic and diverse niche that I find fascinating to study. You have the potential for more swamp-like features, more stream-like features. You can have large channelized systems, and along the margins, all of these factors can act to influence the type of biology you see in these systems. Okay, so I think I went over this, but in subglacial environments, we see every type of microbial metabolism we look for except photosynthesis, of course, because sunlight doesn't penetrate that deep. And we know this from the samples that we've studied, but also from the materials that are released from subglacial environments. Because these microbes are actively participating in biogeochemical cycles, they liberate iron and silica, they release CO2 and methane in their metabolism. And this flux can impact the larger, broader ocean and global ecosystem. So the last few sites are grounding zones, and this is the point where the glaciers and ice sheets that we've just been talking about start to float on the ocean, and I consider this kind of a critical zone. It's where ice, ocean, and sediments interface. And it's a transition area, right, between your subglacial zone and your proglacial ocean cavity. You have the drainage of subglacial fluids and materials coming into this zone, and you interface with ocean chemistry and potentially biota, and it's also a sensitive point of ice sheet stability. In the very few grounding zones that we've been able to explore in the Southern Ocean, it's been really surprising. These are just some images from subglacial Lake Willans grounding zone, and I don't know if I'm going to blow up the internet, but you can see here you have like active fish and a variety of creatures that are living in this ice cave. We consider this the southernmost marine community detected so far. It's a large ice cave. It's about under 759 meters of ice, and it's only about 10 meters of seawater here, and it's about 650 miles from the ice edge. Okay, last realm is ice shelves, and these are now the floating tons of that ice that extend from the grounded glaciers that are on land. And ice shelves surround about 75% of the Antarctic's coastline, which is equivalent to the approximate size of Greenland. And I thought the planetary folks might enjoy this image. This is a picture of the Wilkins ice sheet collapse. And while we're still learning a lot about the physical dynamics that drives this, including melt from the top as well as warming from the base, we are seeing from an ecological standpoint that the distribution of these bergs can then redistribute nutrients into the ocean, open ocean, and provide new nutrients to phytoplankton broadly. Okay, so I think I got within 20 minutes. I got a couple more slides. So broad conclusions is, one, microbes can interact with ice. They can change its physical properties, and this is through their capabilities, including creating extrapolymeric substances and biofilms. They can generate proteins that interact specifically with ice. They can generate and absorb heat from their pigments, and this all in turn can change the physical structure of ice. Ice is an important structure that can support a diversity of life forms, both within it, on it, and below it. We have evidence that this life is visible from aerial footage, like those brilliant pink snow algae I showed you pictures of at the beginning, or they can require really intense ultra-clean investigations, which are technically challenging to actually see the physical structure of a microbe within a small ice vein. The full spectrum of metabolic diversity seems to be found in these systems, and these ice environments, I hope I've convinced you, are actually surprisingly diverse. And each realm offers trade-offs. If you're on the surface, you have the energy from sunlight, but if you're in the subsurface, you might not have that energy. You might have to grow slower, but you're protected from radiation, and you have this sustained source of energy from your rock-water interactions. We were asked to conclude with a slide projecting to the opposite talk, and so this is an Earthbound microbial ecologist's thoughts on ocean worlds with all the caveats. But when I look at images like this picture of Enceladus from ESA, artist rendition, I think of a huge diversity of niche space. And so I think of things like submarine groundwater, subpermafrost groundwater, what might be occurring at the base life that interacts with some form of sub-ice ocean. I think of grounding zones and how those are really interesting ecotones. I think of crevasses and conduits and all the material that can ooze its way through these conduits. I think of perched aquifers that we see in glaciers and snow and how that can accumulate both surface debris and end glacial debris. And I also think of how we study analogues here on Earth, and that these might help us in where to search and how to search. And so a feature I spend most of my time thinking about is a place called Blood Falls in Antarctica. I mentioned it briefly earlier, but this is where this briny marine water episodically discharges to the surface. And so it provides this analog of what happens to material that is ejected onto an ice surface, and we can analyze it for what happens. Now here on Earth, which is nowhere near as detrimental as material coming out on a place like Enceladus or Europa, we still see a significant loss of all the biomolecules and material that are released from this site, but there are little bits and pieces that we can tease out. And so I find this a really interesting feature to think about, not only how we can detect biosignatures on the surface, but also at depth, and what tools we use to sample this system. So with that, the Earth's cryosphere can hopefully inform where to search and how to search. If we go to these other worlds and we're only scratching the surface or the near surface, what types of patterns of deep ice life can manifest at the surface and help guide us where to drill? Where are some of those interesting niches? What type of technologies are used on Earth, right? We've been exploring both hot water drilling, which is unfeasible elsewhere. What about melt probes? We can also test out some of our planetary protection protocols, such as what happens when you drill through ice and what are you dragging with you? Are you inducing some type of spacecraft-induced special region? And while there's no perfect analogs, I still think it's informative to study these earthly analogs, because for a long time we thought life had to pass through this ice filter of snowball Earth and couldn't survive. And then in the past few decades, our understanding of the ecology of icy ecosystems has really exploded. So yeah, with that, I'd like to thank you for your time. Want everybody to stay safe out there. I'll take any questions.
Thanks, Jill. That was a really terrific
unshare?
talk and a great introduction to the series. I will caution everybody not to speak real quick. We amazingly are supporting 130 people on a system that has had trouble supporting 6 people this week. And so we have time for it's great. We have time for 2 or 3 questions. Because there's so many people, I think we should try and use the hand raise feature on WebEx. But if you're just really antsy to ask the thing on your mind right now, I won't ding you if you go ahead and unmute and interrupt. Okay. There's not. Okay. Oh, I see. I am scrolling past people with their hand up. It looks like Cynthia has her hand up, and so does Morgan. Oh, Morgan actually has messaged me about questions. So Morgan, take the first question.
All right, awesome. Great talk, Jill. Thanks so much. You mentioned that microorganisms can alter some of the physical structures and other properties of ice, and I'm wondering if any of that could be detected sort of at the macro level, like say from orbit or from a flyby, or if it really would need to, you'd have to be like in situ to be able to note those differences.
Yeah, I think that's a really good question. I don't know that the research is there yet to know what it might look like from a flyby, but I think even at a surface level, you should be able to see evidence of material that may be involved in restructuring, right? Like EPS, for example. That is something that I think you can detect with at least some of the instrumentation that I've seen in various talks. But from an orbital level, in a crazy world where you had ice algae, for example, living on the surface of another world, you would expect potentially characteristic either pitting or melt spots that were indicative of something potentially melting that area. So I would think that there's, I'm rambling a bit, but I think that if you think about what the conditions are on your planetary target, and you think about what might be feasible, you would expect particular patterns, right? So from space, we can see, like near, like maybe a drone, you can see cryoconite holes, you can see snow algae, and you can see some of the distinct melt patterns that they create. So it's not my area, but I think with more work, something like that is definitely an interesting place to look.
Cool, thank you.
Mm-hmm.
Okay, because Cynthia will get her time to talk, there was one more hand raised from Seth Parker, so I'm going to let Seth ask their question.
Hi, Jill. Thanks so much for the awesome talk.
Thanks, Seth.
I guess my question is, we were talking about the grounded glacier on the edge of the ice sheet. What kind of dimensions are you talking about there? Because I know with caves, like terrestrial caves, the issue is that, a cave is, quote, basically any space a human can fit inside of. So when you say a grounded portion, is that any size that a submersible can get inside of, or are you talking like millimeter strength that at a certain length or certain dimension? I would assume this is more of just a melt effect than an actual, like, quote, cave feature.
Yeah, that's a great question. And I think then, based on that definition, ice cave may not be correct. But think about the entire coastline that the Ross ice shelf floats off. So this is hundreds of miles. And as it takes off of land, you go from grounded ice to steadily increasing the size of marine water in that cavity. So we were about a kilometer from the physical grounding zone, and there it was 10 meters deep. But if you were to go in closer, you would get shallower and shallower and shallower in your marine water until at some point you were actually on grounded ice.
Okay, awesome. I just didn't know if there was kind of a hazy boundary line between like when it's actually a glacier sitting on like a film of water versus when it becomes ice in like more of an open like saline situation.
Yeah, and many of these grounding zones, they have, and a physical glaciologist can speak to this better, but they are subject to some changes from tides, and they're also subject to a movement of their grounding zone. So this is a dynamic region. It's not necessarily fixed in space and time.
That's awesome. All right, thank you so much.
Yeah.
Okay, that brings us in amazingly to exactly 30 minutes from the start of Jill's talk.
Thank you.
So thank you again, that was wonderful. And with that, I'm going to hand it over to Cynthia to introduce herself.
Great, give me a sec to get everything running here. So hi, I'm Cynthia Phillips. I'm a planetary geologist at JPL. And thanks, Jill, that was a really fabulous talk. And I think it's a little bit interesting that that you chose to focus on cryospheres when I, the planetary geologist, am now going to try focusing on oceans. So we're kind of each doing what we think the other community might want. But I do think that these two topics will be very complementary. All right, so let me get this started. All right, can folks see that okay?
Yep, that's the right view.
Looks fine, okay, great. Okay, so I will be talking about ocean worlds in our solar system. So when we think about ocean worlds, we're talking about places where liquid water is present either at the surface or in the subsurface. So here's a diagram of confirmed and potential ocean worlds. The only ocean world that we have that actually has an ocean at the surface is the Earth. And so when we look at the rest of the solar system, the Earth turns out to be kind of weird, and I'll come back to this a bit more at the end. But on the Earth, we have liquid water that's actually stable at the surface. We have an atmosphere over it that has enough vapor pressure to keep that liquid there, keep the temperature above the triple point of water. And so we have this weird layer of liquid. And I say weird because if you look at the rest of the solar system, the way that a, quote, normal ocean works is that these normal oceans are below the surface. They're subsurface oceans. And so I'll be talking about worlds in our solar system that we know, that we think have liquid water somewhere in their subsurface. And so in this diagram here, we have worlds like Mars. Mars doesn't have any liquid at its surface today. It might have a little bit in the subsurface, but we think that back in the geologic past of Mars, there was actually a large ocean in the northern hemisphere. I'm not going to talk about Mars much in this talk because I'm really looking for current ocean worlds. We have some small bodies like Ceres that could have a subsurface ocean. But really, we have sort of the canonical ocean worlds, which are moons, are satellites of Jupiter, Saturn, and some others out in the outer solar system. And so if we move on, here are the worlds that I'll talk about in this talk. And these are all to scale with the Earth. So Jupiter's moon Europa is kind of our type example of an ocean world. And then we also have Enceladus. And so when I go through Enceladus in a minute, keep your mind on how small Enceladus is. It's really a very, very tiny world, and yet it's way more interesting than, in my opinion, it kind of has any right to be. So we'll go through Enceladus, a couple moons of Jupiter, then we also have moons of Saturn, Titan, then I'll talk a little bit about Triton, which is a moon of Neptune. And there are other potential ocean worlds as well. These are the ones that I'm just going to focus on today. So I'm going to start with Jupiter's moon Europa, not just because it's my favorite place in the solar system, but because really Europa is the place that really started us thinking about ocean worlds. So it's a moon of Jupiter. It's about the same size as Earth's moon, but the surface is covered with very different feature types. It's covered with cracks and ridges that if you zoom in, you can see we have these ridge planes. So these are long linear features. They are a couple kilometers wide. They're maybe a few hundred meters tall, but they stretch for thousands of kilometers across the surface, as you can see in the global picture. And then in addition, we have places in the surface where the surface has been disrupted into what we call chaos terrain. And so these look a lot like those icebergs that Jill showed in the previous talk in the breakup of that ice sheet. And so you can see the scale bar on the bottom of 20 kilometers. So everything on Europa is at a much larger scale than anything that we see in terrestrial ice. However, there's a lot of analogs, we believe, in what's going on. And Europa's surface is also very young, and we know that. So that's geologically speaking. So in terms of the age of the solar system, we think the age of the surface of Europa is about 50 million years, maybe plus or minus 50. And we can tell that because there's very few impact craters on the surface. In this picture, you can just see there's just two of them. There's two big ones. There's one here and there's one here. But other than that, the surface is really covered with other feature types. So if we go on and look at Europa, we think that Europa has the planetary ingredients for life. And so those are things like liquid water, the right chemical elements, but more importantly, we need a source of energy. We need some kind of energy gradient that can drive the chemical reactions that can lead to, the origin and the survival of life. And then stability is kind of the fourth data point here. We think that from what we know about the origin and life of Earth, which again isn't much, we only have one example on Earth, but we think that you need all of these three conditions to be met for a long enough period of time that whatever happened to start life has time to get started. And so Europa is a great place to look for those things. If we look at the interior, we know from spacecraft data that there's a layer at the surface of Europa that's about 100 kilometers thick. It consists of some portion of solid ice and some portion of liquid water. And this comes from gravity measurements taken by the Galileo spacecraft, as well as data that we received from the magnetometer and other lines of evidence. So this is an indirect detection of the ocean. All of the potential ocean worlds in our solar system are in some way indirect detections. We have not yet drilled down through the surface to actually swim around in that ocean. So while we think a lot of those oceans are there, and in the case of Europa, we're really pretty sure that that ocean is there, we have not directly detected it yet. But what we can see on Europa is that the interior, so we have this ice layer, we have a water layer, and then the water layer, the bottom of that ocean, is touching the silicate interior, so the rockier interior of Europa, and then we have a metallic core way down in the middle. And so what this tells us, if we just zoom in, and again, this is not really to scale, but we have an icy layer at the top, we have a large ocean of liquid water. We know from the measurements of the conductivity of this water layer, we know it has to be liquid, and we know from its conductivity that it has to be salty, but not too salty. We're talking even a little bit less salty than Earth's oceans, which are abundant with life. But at the bottom of this ocean layer, where at the water-rock interface, we could even have hydrothermal systems, so similar to what we find at the bottom of Earth's oceans. And so when Jill was talking about potential niches for life, so places where life could survive, we have this water-ice interface at the top of the ocean, and then we have this nice water-rock interface at the bottom of the ocean. And so we think that that ocean is kept liquid through tidal heating. Basically, the moons of Jupiter, Io, Europa, and Ganymede are in a resonance, so it's a 1 to 2 to 4 resonance. So every time Ganymede goes around once, Europa goes around twice, and Io goes around 4 times. Because of this, you have a forced eccentricity. And so Europa's distance from Jupiter changes over the course of its 3.5-day tidal cycle. And so the surface gets stretched and tugged by Jupiter's gravity, and this tidal flexing produces tidal heating. There's enough heating to actually keep an ocean on Europa liquid over the age of the solar system. And so, again, I'm going through Europa in a bit of detail because it's really the type example of an ocean world, and many other places in the solar system, many of these other ocean worlds that I'll talk about, really follow a lot of the same story. So on Europa, if we look at a hypothetical cross-section, again, we have this liquid ocean layer. In this estimate, an ice layer is maybe 10 kilometers, 20 kilometers thick. It could vary. It could be thinner in some places, thicker in others. And then below that, we have, 100 minus that thickness. So in this diagram, it's about 100 kilometers of ocean, maybe a little bit less if the ice layer is thicker. And at the bottom, we have a rocky interior. So we could have analogs to Earth's hydrothermal vents down here at the bottom. We could also have multiple places within the ice layer itself that start to make analogies towards some of those great niches for life within ice sheets on the Earth. So probably not at the surface. The surface of Europa is, it's not just a vacuum, 100 Kelvin going off into space, but it's bombarded by radiation. And so that radiation would not really allow for the survival of life at the surface, even if it could live there otherwise. But once we get into the actual ice layer, we think that there could be pockets or sills, maybe subsurface lakes of liquid within this ocean layer. Maybe there's places where warmer ice rises up, something like diapirs. There certainly are cracks and ridges that we've seen. Maybe there are conduits for liquid to work its way up through the ocean and maybe vent out into space. There's been potential detections of plumes on Europa, although we don't have any definite confirmation of those yet. And so is Europa's ocean habitable, and could it be inhabited? So could life survive there is a different question from, is there actually life there today? And so really to answer these questions, we're going to have to go there and find out. And I'll talk a little bit about missions at the end of this talk. But one very simplified way of sustaining an ecosystem on Europa could be if you have radiation-produced oxidants at the surface, which then can work their way down through this ice layer into a salty ocean. Depends on the circulation of that ocean, but you could produce interesting reactants, say if there's hydrothermal systems at the bottom of the ocean, that could give you a nice gradient and a nice source of chemical energy, perhaps to sustain an ecosystem. So let's move on to a few other places in the solar system. Saturn's tiny moon Enceladus, it looks a bit like Europa in that we have these long, linear, kind of crack-like features, and at least in the southern hemisphere, there are relatively few impact craters. So again, that tells us it's a relatively young surface. But what's really striking about Enceladus are these plumes. So on Enceladus, we have a definite actual detection of plumes that are venting material off into space. And so this is similar to the image that Jill showed, where basically we have an icy crust at the surface. We have what we think is a globally interconnected ocean layer and then a rocky core in the interior. And the south pole of Enceladus is where we see these active jets, where material is actually being vented off the surface into space. And Enceladus is so small, its gravity is low enough that this vented material actually forms a ring around Saturn. So Enceladus orbits Saturn within the E-ring, and we think that that E-ring is made up of the particles that have been vented out of these plumes. And so if we look at, again, a cross-section of Enceladus, so again, look at the construction here. So we have a surface ice layer, maybe even thinner than Europa's. We have a subsurface ocean layer that we think could be global in extent. And then below that, the ocean, again, is in contact, we think, directly with a rocky interior. So Enceladus, too, is a place where we could have hydrothermal circulation. We could have interesting interactions with the subsurface, the ocean layer, and then clearly there is access from the ocean out into space. So moving on, we can look at Saturn's moon Titan. So Titan is a weird world because it has this thick hydrocarbon-rich atmosphere at the surface. And so it's this thick, hazy atmosphere that makes it very difficult to see all the way through to the surface. We have actually landed on the surface of Titan. The image on the right was taken by the Huygens probe, which landed at the beginning of the Cassini mission. And so what we see on the surface of Titan is a world that's dominated by hydrocarbons, by ethane and methane. And so while we think there is actually a cryosphere there, or a hydrosphere, I don't know what you call it, maybe an ethosphere, right? So it's basically a world where you have recycling of hydrocarbons. You could have rain, you could have liquid lakes of ethane or methane on the surface, you could have percolation, you have carving and erosion that's caused by these liquids moving on the surface. And here on the surface of Titan, water ice is like a rock. And so these things in this image that look like rocks, look like pebbles, these we believe are actually chunks of water ice that serve the purpose of rocks in this very weird, system at the surface of Titan. But I'm looking at oceans, and to me an ocean has to be made up of water. So these ethane and methane lakes, they don't count in my book. Fortunately for oceans, if you go into the subsurface of Titan, if you ignore all that weird chemistry going on the surface, you find a nice water ocean. And so Titan, we believe, actually looks a lot like these other ocean worlds. So you have this thick layer of ice at the surface, and below that ice, we think that there's a relatively large global subsurface ocean. But interestingly, Titan is a very big world. It's one of the biggest satellites in the outer solar system, and so this ocean layer is sandwiched between two ice layers. You have an outer ice layer that's probably more like ice 1H, but then on the inside you can have a high pressure form of ice. So this is ice 6 in this model. And then you have a hydrosilicate core in the middle, so a rocky core in the middle of Titan. And so this ocean is different from the ones we've looked at previously because it's sandwiched between 2 ice layers. And this is going to become a theme as we look at the other oceans. But so again, on Titan, we have that thick atmosphere and surface. You have some weird liquid processes that are going on here at the surface. But then if you go below, you have a decoupled ice crust layer, a global subsurface ocean, a high pressure ice shell, and then below that a hydrated silicate, so a nice rocky interior. And so it's possible that you could have interactions in this ocean layer with the core, but because you have this ice layer at the bottom of the ocean, that makes it a lot more difficult. So if we move on to Jupiter's moon Ganymede, Ganymede and Titan kind of fight it out for the largest moon in the solar system designation. It depends on how much of Titan's atmosphere you include in its radius. But Jupiter is certainly the most massive. Ganymede is the most massive, certainly. It's actually bigger than the planet Mercury. And so if we look at Ganymede, we can see the surface is covered with older terrain. So now if we compare what the surface of Ganymede looks like to those images that we saw of Europa, Ganymede's surface has a lot of craters. It does have some kind of ancient terrain. There's things called grooved terrain. So you can see here in this image, we have areas where there do look like there's some kind of ridges or bands, maybe tectonic activity. We have some weird scarps on the surface, but again, there hasn't been any activity on the surface anytime recently. And so if we look at models for the interior of Ganymede, it's pretty similar to Titan actually, where you have a relatively thick layer of ice at the surface. Below that ice, we think there's a fairly large ocean. It's probably salty like Europa's ocean. But below that, we have another higher phase ice layer, higher pressure ice layer. And then on Ganymede, we know there's a rocky mantle, and then it's fully differentiated. So we know that it has a liquid and a solid internal core, and it generates its own magnetic field. So in that way, it's a lot like the Earth, where it has its own dynamo. If we look at another proposed model for the interior of Ganymede, that's sometimes called the club sandwich model. This one's amusing because you basically have layers of ice, and then you have liquid ocean layers. And so as you go down, you go to more and more higher pressure phases of ice. So you start with ice 1 on the exterior. We go down into kind of a snowy ice 3 layer, and then ice 5 and ice 6. But in between each of these layers is a layer of kind of briny, saline liquid water. And in this particular model, as you get to the bottom, there is a very salty layer of water that's in contact with the interior, the silicate interior, so the rocks at the bottom of that ocean. This is just one speculative internal model, and when you look at this, there's some questions about how stable this actually is. So this might not hold up over geologic time. It might be more of a transient effect, but it's kind of a cool thought experiment to think about here. We can then move on to Jupiter's moon Callisto. Callisto is another large moon. It's covered with craters. Really, the only activity you see is a little bit of frost moving around on the surface of Callisto, but it's really an old crater body. Even somewhere like Callisto, though, there could be a subsurface ocean. It's just much further down. And you'll note I don't have numbers on a lot of these, and that's because all of these internal models are very speculative and they're very model dependent. But if there is an ocean on Callisto, it's probably relatively large, but it's very deep. And one interesting thing about Callisto is that it's possible that it's only partially differentiated. So that means you could have an ocean layer, you have a surface ice layer, you have an ocean layer below that, you have another higher pressure, maybe ice 5, or a mixture of rock and ice in this particular model of ice 6. As you go down, you have other mixtures of both rock and ice before you get to this is a partially differentiated model, before you get into this rocky and metal core at the center. So again, possible ocean, pretty large in volume, but there's no water-rock interface in this model. It just goes ice, water, ice. Neptune's moon Triton is the last of the moons that I'll cover in detail here. And Triton is this gorgeous moon of Neptune that we saw during only once, so during the Voyager spacecraft flyby. And so when we look at Neptune, we can see that it actually is pretty similar to Pluto. I'm not going to talk about Pluto in this talk, But when we look at Neptune and zoom in a little bit on the bottom of that previous image, we can see that Neptune was actually one of the first places it was the first place that we found cryovolcanism. Jupiter's moon Io does have volcanic activity, but what we found on Triton was that there are actually plumes or geysers of what we think is nitrogen being ejected from the surface. And you can see in this image, you can see 2 of these are indicated where you have a geyser, you have a material being ejected, lofted up above the surface, and then kind of blown into this prevailing direction. So you can see these 2 dark streaks. These are these parallel lines, which then give you dark deposits on the surface. And so once you know what to look for, you can look at a bunch of these smaller ones. So many of these are little nitrogen plumes that are active or recently active and have left these plume deposits on the surface. And so Triton 2, we believe, could have a subsurface ocean layer. So when we look at these worlds, when we look at oceans in the solar system, we always think of the Earth because of all of the Earth's water is right there on the surface. We think of Earth as our ocean world. But if you look at the amount of water, both in terms of the absolute number as well as the percent by volume, this is kind of misleading. So if we take all of the liquid water, so this is not counting frozen water or vapor, just liquid on Earth, we scale that to this size here. So this is the amount of Earth's water. Europa has more than twice the amount of water in all of Earth's oceans combined. Ganymede is more than 6 times, and then Titan's up as high as 11 times. If we look at little Enceladus, it doesn't have very much water in terms of absolute, but if we look at the percentage of liquid water, it's up at maybe as high as 14% liquid water. So because Enceladus is so small, that little ocean is huge in terms of the percentage. So if we then take a look at these interior models, I've gone through a number of these in detail. There are others like, Pluto and some of the minor planets like Sedna and Eris and Ceres that we think do have oceans as well as other satellites of Saturn, Uranus, Neptune. But when we look at these again, we're thinking about key niches for life, key places where either chemical reactions could happen that could sustain life, or places where life itself could live. We think that having this water-rock interface is really key. And so when we're looking at that, we're really left with Europa, which has that rock layer at the bottom of the ocean, and also Enceladus, which we also think has this water-rock interface. So I'm just going to talk for just a minute about exploration of these worlds. As a planetary scientist, I have to throw in some missions. So we look at our ocean worlds, and so this categorization from the NASA Roadmap to Ocean Worlds basically sorts out some of these destinations into either pretty probable ocean worlds or possible ocean worlds that have been less well confirmed. And so in the probable category, we've identified kind of a list, so an increasing list of the way that we would look for life on these places. And so we would start by looking for energy sources, ocean signatures to confirm that ocean is actually there. We'd want to look for the correct solvents, materials circulating, see whether or not there's a rock-ocean interface, and then we look at the energy for life, the chemical conditions, and then finally a search for life with actual biomarkers. And so if we look at this chart, we can see that we have a couple of really interesting upcoming missions. We have Europa Clipper, which will be launched sometime in the 2020s to explore Europa. This mission will not land on the surface, but it will do a lot of characterization of Europa from orbit. We also have the Dragonfly mission, which will explore Titan with multiple landings on different locations on the surface of Titan. And then we have the European JUICE mission, which will explore Ganymede. And so as we move forward, we'll really be able to think about where we've been. So here are our first round of missions. So we've had Voyager, Galileo, Cassini, Dawn, and New Horizons that have done sort of like the first level, the reconnaissance flybys of these worlds. And these are the ones that really detected and told us that ocean worlds did exist in our solar system. We also have planned ocean worlds missions. So again, we have JUICE, we have Europa Clipper, and we have Dragonfly. These are all planned for launch later sometime in this decade. And then we have a variety of proposed missions that would actually, say, fly through the plumes on Enceladus or land on the surface of Europa, and eventually would be able to get into the subsurface, get deep below the surface, and maybe actually access those oceans directly. And so, just like Jill did, I was asked to think a little bit about what ocean worlds can tell us about Earth's ocean. And so Jill and I did not coordinate on this at all, for which I apologize because I am not at all a terrestrial oceanographer. So these are just my thoughts. Earth only has one ocean, you know, and it's a great ocean. I'm not knocking Earth's ocean, but studying ocean worlds would help give us a diverse set of initial conditions. So how oceans could work, other ways that oceans could exist. It's also possible that ocean worlds could help us could help represent different phases in Earth's history. For example, during a snowball Earth condition, like Jill mentioned, when we did perhaps have an ice-covered ocean on the Earth, we can look at ice-covered oceans that exist now elsewhere in the solar system to help understand how those oceans might work. Ocean worlds could also represent extremes or end members that are not found on Earth. Things like stratification of an ocean, extremes of salinity and composition when you look at what are the non-water components in these oceans. And they can also help to inform circulation models as we look at the vertical and the horizontal transport of water and the dissolved materials in that water. And then finally, if we think about biology, if we do life on an ocean world, we're going to have a second data point for the origin of life. And so it's really interesting as we move forward and we think about, well, we don't know how life formed on Earth, but if we could come up with 2 data points, not just one, then that would allow us to say, okay, what do these 2 worlds have in common that can help us pin down, you know, how important are hydrothermal systems? Can life form in the deep subsurface, or does it need to form more close to the surface? Can life form independently of sunlight? And so I'm really looking forward as we continue to explore Earth's oceans and Earth's cryosphere, in conjunction with our exploration of ocean worlds in the solar system. I think there will be really amazing synergies between these 2 fields. And that's what I have for now.
Thanks so much, Cynthia. That was a really terrific ocean world summary. And it's fine you didn't coordinate with Jill and you're not a terrestrial oceanographer. You were asked to give this talk because you're not a terrestrial oceanographer. So we do have time for questions on Cynthia's presentation if we're okay to hang out on WebEx a little longer. I kept the meeting open for another half hour, so we should be fine. So with that said, I will first scroll to see if anybody has their hand raised, or you can just comment in the comment section that you would like to ask a question. Might be easier than me scrolling through 130 people. But it doesn't seem anybody is raising hands. So I have a question. Oh, wait, there is one. Maybe. I have a question, Cynthia.
Hello. Morgan has one too, but after you, Sam.
So Cynthia, from your perspective as a planetary geologist, what of these missions that are going to begin science return in the, 30s are you the most excited about? Again, from the perspective of planetary geology as it relates to ocean worlds, more so than the oceans or life.
Well, that's an easy question to answer because Europa is my favorite place in the solar system. So, as unbiased as I try to be, I just can't wait to see new pictures of Europa. And, hopefully we'll get to see those by the end of this decade, maybe a little bit into the next, depending on what kind of rocket that mission gets to go on. But Europa Clipper is just going to be just a fabulous mission that will focus on Europa with not just cameras. I specialize in image processing, so I want to see those pictures. But there's also other great instruments that will tell us about the composition. We'll have a radar instrument to be able to sound the subsurface, maybe do a direct detection of the bottom of the ice layer, so of the ice-water interface if we're lucky, as well as in situ instruments that will be able to measure the composition of material that's thrown off the surface of Europa. If there are plumes on Europa, Europa Clipper will be able to fly through them, but even if there aren't plumes, enough material to spurt off the surface through impacts of dust and charged particles that will be able to actually taste the composition of Europa from orbit. And I just can't wait for those observations.
Perfect. Nice softball question to get going. Morgan?
Hi, Cynthia. Fantastic talk. I really loved the synergies between some of the things that Jill spoke about and some of the things that you spoke about. And in your last slide, you talked about how ocean worlds could be used as sort of end-member cases to inform our understanding of these places in general. But I'm wondering if, since I think we still have Jill on the line, some other cryosphere-focused people here that focus on Earth, are there any things that we can take from those studies? So like what would you like to see in terms of cryosphere science that could help inform future Europa or Enceladus missions?
I'm sorry, so was that question for me or for Jill?
Well, I would like to hear what both of you have to say, but I'd love to start with you, Cynthia. Like, is there any particular thing that you think we could take from Earth that would help us better inform either in situ or orbital type of mission of what we might want to look for, or things that could help us avoid bad situations for some of our in situ missions?
Yeah, so I think that especially when we start thinking about, say, landing on the surface of one of these worlds, there's just so much we don't know. And I think that looking at terrestrial analogs on, icy locations on the Earth, they're not perfect, certainly, but I think that they're kind of the best we can do in a real-world scenario. And so I'm really interested to see further characterization of icy surfaces in terms of topography, in terms of the surface processes that are going on, in terms of interactions with the subsurface. One of the things I'm really interested in is whether what we see at the surface, that's usually what we see through the so-called remote sensing layer. So most of what we can see from orbit is really of just the top couple microns of the surface when we're talking about composition. And so I really want to know how what's seen at the very surface relates to what's seen in the subsurface on terrestrial icy environments.
Yeah, and if I would just chime in and second that, I think that's a challenge that we face just studying the subglacial world, because it's so hard to get through to the subglacial realm, that I'm also interested in how does subglacial material migrate through ice, and how does it survive at the ice surface, and how can we ground truth what we see in satellite and radar imagery taken remotely to what we actually see on the ground and in the near surface.
Very cool. Thank you both.
I'll also mention from the chat that Allison McDonald brought up that in these drawings, the ocean silicate interface is always very flat, and asking whether or not there's any reason to actually believe that the interface between oceans and rocky layers and planetary systems is flat. Chris German responded in the comments that it's easier because we have no idea what they're like.
This is Murthy here, Murthy Giripati speaking. One thing that is interesting and important to compare between Earth's cryosphere and ice of outer solar system in terms of habitability is also how ice and non-ice material mixes. We know that most of crystalline ice expels any impurities in it, and you need to have, as I heard from Jill's talk, small. Sorry for that. This is how it is if you stay home and work. So that's important to understand how non-ice and ice material interact with respect to temperature, with respect to pressure, whether we have veins, how long they are, and pockets. All these things are important to understand from cryosphere, Earth's cryosphere work or other ocean and ice containing bodies.
Yeah, and to go back to Allison's question, I have another response to that, which is that really all of the models just use a flat, rocky layer at the bottom of the seafloor, relatively similar, so consistent thickness of each layer, just for ease in modeling, because we really don't have any other information.
Cynthia is muted. You're muted.
Sorry, am I still muted?
No,
you weren't.
I don't actually think you're.
Cynthia.
Yeah,
okay.
You weren't muted.
So while it's often expedient just to use consistent layers as we go through and do this modeling, just in the lack of any other information, but it is interesting that one of the things people are particularly interested in for Europa, especially, is the ice layer a constant thickness, or are there places where the surface ice layer is thinner versus thicker? And so that I would say is something that's up for active debate. Of course, if we're going to be observing Europa from close orbit with Europa Clipper, or if we're going to be looking at possible landing sites for a future landed mission on Europa, ideally we'd want to land in a place where the ice was as thin as we could get it. And so there's some folks who do think that there are places where the ice could be thinner. However, there's also models that show that say if you had sort of a reverse iceberg, so an underground or a mountain, an upside down mountain, a big lump sticking out of the bottom of the ice layer into the ocean of Europa, some models do show that while that would affect the local circulation in the short term, it looks like in the long term that lump would be worn down pretty quickly. And so there are some models that show that basically any thickness variations in that ice layer would not be stable over geologic time, and so you would tend toward an equilibrium situation with a constant ice layer. That still is, it has not yet been proven. It'll be really interesting when we go there with Europa Clipper if we are able to sound all the way through the ice layer into the ocean to see if there are variations in ice thickness. And I personally am hoping that there are places where it's thinner, because that's where I want to put a lander, but we'll have to see.
I would just add, I was pretty excited about Cynthia's talk on the layers of rock and ice, and sometimes layers on layers of ice and ocean and sediment. And on Earth, we do see a lot of topology below the ice, and associated with lakes, we have mountain ranges like the Gewächshaft, deep lakes, shallow lake streams. And so, when I saw that layering, I saw the potential for diversity there. I don't know how that works on a planetary scale, but that seemed interesting.
Okay, so there was one hand raise for Cynthia from Chris German, and then I think we'll wrap things up.
Thanks, Sam. Cynthia, something I'd never seen before was you made a comment about how Ganymede and Triton looked quite similar to each other in cross-section. And it just made me think of a question I haven't thought about at all, which is there a really good understanding of then why Triton has all its organic stuff on the outside and Ganymede doesn't have that? Is that something to do with volatiles in the solar system, and one's a moon of Jupiter or Saturn, or?
Yeah, no, that's an excellent question, Chris, and I would say the answer is no. Certainly people have speculated, but I don't think there's any definitive theory I've seen that really explains why Titan has this humongous, gigantic atmosphere and no other moons in the solar system do. My guess would be it's primordial, right? So when Jupiter was forming, my guess would be, and this is, me speaking as a planetary scientist, but not as an expert on Titan. I think we have some Titan experts online who can correct me if I get anything horribly wrong. But my gut is kind of, you have Jupiter forming, and Jupiter is, it has more mass than all the rest of the other planets combined, right? It's this gigantic sort of greedy world, which fits with Jupiter's kind of role in mythology as well. And so if you take Jupiter, it sucked up all the gas that it could get. And so probably my guess would be that there just weren't that many of the lighter elements, those volatiles, left when the satellites formed. In the case of Saturn, Saturn is also pretty big, but perhaps it's that it's not as big. And so some of those volatiles, some of those gases were left And Titan is also, the Saturn system is different from the Jupiter system because Titan is the only big moon of Saturn. Basically, you have Saturn, you have Titan, and then you have, a bunch of little tiny moons and ring particles and stuff. And so, it could be that Titan was able to grab more of this material just during when it was formed. There's other theories where, could you have some kind of weird impact that would have brought this material there? But yeah, I think it's really an open question. I don't think there's any excellent definitive answer that says, yes, this theory explains why these two worlds are so different.
Thank you.
So on that note, I'm just going to add on to there before I close, only because I like the Titan-Ganymede comparison. The one thing I often think about Ganymede is because it's so large, the ice shell is likely to be as geologically active as Europa's, just hidden from space because of a thick, cold lithosphere and a very thick ice shell. But, it could have internal convection and all these fun stuff. So could Titan. And I like to wonder, is it possible life emerged twice on Titan, once in the ocean and once on the surface?
Now I'm just getting greedy. I think there's a great quote. I think it was from Jeff Moore, who said that I think it was Jeff who had a paper that said that Titan is basically Callisto with weather, and I kind of like that.
Great. Well, so I'm going to thank Cynthia and Jill again for being our guinea pig speakers, especially in these uncertain times, and thank our co-leads, Allison, Alyssa, Chris, and Kevin, as well as the co-organizers of the lecture series, Shannon, Ella, and Laurie. And so with that, we will wrap up our episode 1, and please stay tuned for future iterations.
Thank you.
Bye, everyone.
Thanks.